Welcome to Wireless Future. This is episode 38. I'm Erik Larsson and I'm here as always with my colleague Emil Björnsson. Hello Emil, how are you this morning?
I'm great, and I'm feeling well sitting inside now when it's so cold outside in Sweden in this part of the year.
Yeah, indeed. So any snow up there in Stockholm?
Yeah, we have plenty of snow outside here. I can see through the window.
Yeah, we also got quite a bit here. So great to be back recording, Emil. This episode, so the intention was that we'd talk about the 6th Symposium that was held last month in Lund and that we both attended. So what were your impressions, Emil, from that symposium?
Right, so this was a great symposium, I would say, and it was a 3-day event. And I think in the last episode, we had like a panel discussion with a number of speakers. And I was thinking that I was able to gather a lot of good speakers in Stockholm for that event, but it was like 3 times more people in terms of great speakers there in Lund. So it was a really great event, I would say.
Indeed, I mean, the event had really an array of distinguished speakers and also a very good audience, I think. So I enjoyed a lot participating and I learned a lot of things. And the plan, I think, for today was that we'd talk about some things that we learned there.
Yeah, exactly. And as usual, you can either watch us on YouTube, or if you are you only want to listen to this podcast, you can also find it on Spotify and Apple and Google Podcasts.
That's right. So that might be good to know for our followers that we are obviously on YouTube, but the audio track is also on all the major platforms: Google, Spotify, and Apple. I think those are the 3, Emil.
Yes, exactly. And it's always great to meet people at conferences who are listening to the podcast. And we also realize that not everyone is aware of that there are multiple ways of viewing and listening to this podcast. So thank you for listening.
Indeed. All right. So to the 6th Symposium, Emil. So how would you summarize your impressions and the main things that you learned?
Right, so it was an all-physical event, and I think this is really important these days because otherwise when there is a lot of possible online events, people tend to sort of log in and only listening to the things that they are the most interested in, and then you might miss a lot of the things that are not within your main interest area but are really good insights. So I've been collecting my 5 new insights that I collected from this event, and I think you did the same, right?
Yeah, I also collected a few insights. I mean, indeed, I concur that physical events are really superior, and this one again was really super useful and nice, I think. So where do you want to start, Emily, with your insights? Shall we start with sensing and positioning? Because that was a theme that spanned, I think, across several of the talks and presentations.
Right. Yes. So integrated sensing and communication, or ISAC, as people like to call it, this is a topic that I think is one of the research topic for 6G that actually turned into become an important thing in the future. And it's sort of about adding new features to existing networks for sensing purposes, because communication technology, we know what that is, and then we have the additional radar sensing and localization technology that have to a large extent been deployed in a different way. And then on the one hand, you see people in academia writing papers about how you at the physical layer, using exactly the same signals, can do a little bit of communication, a little bit on sensing. But I heard an interesting talk there from Ericsson, Stefan Parkvall, who is one of the leading researchers there. He was talking about their view on how to integrate sensing into communication systems.
So what was their view?
Right. So one of the important things there is that they were categorizing the integration to different levels, where what I was just talking about was sort of the deepest level. So I think one could start with just saying, okay, we have certain sites where we deploy base stations today. What if we deploy some additional sensing equipment on the same location, but next to the base station? That would sort of be the first thing. So co-located deployments.
So you mean basically like a radar station sitting next to an access point? Is that what they meant here?
Yeah, exactly. So from that location, you might be able to send out some additional signals in order to sense the traffic in the environment around there. Typically in line of sight scenarios, you could send something around what happens there. Is there a lot of users? Is there a lot of movements and so on?
Sure, but I mean, that sounds at the surface at least like a fairly rudimentary approach, because you could use the signals from the access point to do the same thing now.
Right. So the second sort of level of integration would be that you are actually using the same site, but also the same spectrum. And normally this kind of technology have been using more millimeter wave frequencies, while we have been used to using sub-6 GHz frequencies for communications. And now when communication is also moving into those ranges, there might be the possibility of sort of using the same spectrum for both things. Then at the third level, we come to what you were mentioning, where you also use the same hardware.
But
so,
I mean, Emil, using the same spectrum sounds a bit like a challenge, because then regulations would need to like permit that you're using the spectrum to communicate and for like sensing and radar, right? So is that already, I mean, do regulations already permit that today, or would that entail a change of regulations for the future?
I think it depends on what kind of frequency bands we are using. I would guess that if you start from using communication frequencies that are allocated for these wireless transmissions of data, then if some of the data signals actually contains known signals, like pilot signals that you use for sensing purposes, you can certainly use them.
That's right.
But if you start to go into that you can disturb other kind of sensor technologies, then I think the regulation will be not permitting that. So it really depends on what band you are using, I guess.
Right, because you could think of like for sensing that you want to probably blast as much power as is possible in every possible direction, whereas for communications you'll be more selective and you'll beamform to your users. Anyways, so that would be the second. Now you said the third way of integrating at an even deeper level.
Yes, so that is to actually use the base station, the same hardware technology, the same spectrum, the same location, obviously, because it's the same base station, but not at the same time or frequency. So you take some of your subcarriers in an OFDM system, and there you blast the signals that you're saying, and you sweep around and look for different targets, and then you use the rest for communication. And it seemed like Ericsson found that level to be the most important one, at least to start with, to make the system work, because then you can add these new features without risking to destroy your conventional communication protocols.
But I mean, that sounds like a meaningful approach, right? Without having thought too deeply about the question. But the equipment is already there. Regulations permit that you use parts of the band for sensing, and provided you have like the spare capacity to you can actually do so, then you'd send some of your subcarriers, you'd send signals only for sensing, or like a radar that just operates within the system, within the communication system.
Right. And I think at this level, they were also considering that you can have the liberty of designing your waveforms a little bit differently, because if you only want to maximize the amount of power you're transmitting, you might like to send something that is more constant envelope, no peak to average power ratio, which you usually get for data signals, and in that way you can sort of increase your power level. While if you go deeper, you can say, oh, we use the same waveform. It is exactly the same OFDM signals that we are using. It's just that on sub carriers we send known signals. And then at the sort of deepest level, we do both of the things at the same time, at the same frequencies. We just say, okay, we send some data in this direction, and we send some sensor signal in this direction, or we reuse the data signals, we receive them somewhere else or at the same location, and we know data signals, we use them as a known radar signal, even if it's actually where data.
So actually reusing signals that are transmitted for communication purposes, also for sensing, by receiving them either like in a bistatic setup, so you receive them somewhere else, or with some sort of full duplex arrangement, I suppose then.
Yeah.
That sounds like an interesting direction to explore.
Yes. And I think from Ericsson's perspective, they were to a large extent viewing this as some new use cases that would sort of separate from the other use cases. So a way of sort of selling, well, we can send data, but you can also buy this kind of extra services. But the topic of sensing was also brought up by some other people in this forum. So say Henk Wiemers, for example, that we had in the previous episode, he was talking about that, of course, with these sensing capabilities, you can also improve some of the things you're doing in your normal communication system. So channel estimation kind of features could be improved if you can, to a better extent, track movements from the sensing systems. Then you can improve channel estimation, predict things, and so on.
Right, because I mean, in a way, channel estimation is a sensing problem, isn't it?
Yes, it is. And I think often there are a lot of nice algorithms that you can use in theory that we teach in courses. Then it is often like that you, in real systems, you want to sort of you restrict yourself to sort of split up time and frequency in sort of ways where you don't have dependencies. You want the scheduler to be able to schedule a user whenever the system thinks it's a good idea to do. So it might be good to use information that is gathered over time about these devices. But this will allow you to do some of these features that clever implementation might already be doing, but in a better way.
Right, I can imagine in practice there'll be lots of practical constraints, like latency constraints, for example, that the scheduler will have to handle, and that could put constraints on when you actually can use this waveform for sensing and when you have to use them for communications in order to meet this latency and targets.
Yeah, but I think the main takeaway from my side there was that, I think localization and sensing will be integrated into the next generation of communication systems, but possibly not in the way that most people are analyzing in academia by having physical layer problems where you do both things at the same time, but actually using the same hardware at different times or frequencies for these features. That will for sure be there, I think.
Oh, that's an interesting thing to know, indeed. Yeah.
And you picked up something regarding positioning as well?
Yeah, so one thing I picked up was that there's a lot of discussion now about positioning using or exploiting phase coherence between geographically separated access points. And that's a real exciting thing in my view, because as we know, if you have an array of antennas and you want to estimate, let's say, direction of arrival, then we know that the accuracy that you can get is essentially like inversely proportional or to the aperture. So larger the aperture, the better accuracy. And with a large enough aperture, we can get angular resolution. We can also get depth resolution, as we know. And now we can build like a virtual or array or an array that consists of antennas or access points that are geographically separated. So that would constitute like an array with an enormously large aperture. Then we could get, in principle, extremely high resolution in angle and potentially also in depth or in range. And this, of course, requires the antennas at these different access points to be phase coherent, which in itself is a major challenge. But given that we can actually achieve that phase coherence, then we could get extremely high resolution down to essentially a wavelength. I mean, what happens here is that we basically measure the carrier phase of the signal to these different access points. If you think of like the likelihood function for localization or the ambiguity function, then nominally without phase coherence, it would have a curvature that's proportional to the aperture per access point. But now that the access points can operate phase coherently together, the likelihood of the ambiguity function rather becomes spiky, like a soccer ball wrapped in barbed wire, with a spike, the distance between the spikes here are on the order of a wavelength, or inversely proportional to the total aperture constituted by all these antennas or access points together. So there was a lot of talking about that, and this is a fascinating prospect, I think, to be able to really use the carrier phase from separated access points together.
So is this like using a distributed MIMO or cell-free massive MIMO system for positioning as well?
That's right. I mean, cell-free massive MIMO or distributed MIMO or distributed antenna system are all names for the same, all mean the same thing, namely access points or antennas that are geographically separated and they can operate phase coherently together.
Right. So this is like integrated sensing communication or positioning and communication for these
I guess it could
networks.
I guess the positioning could be integrated with the communication somehow, but even if the system were used only for positioning, it's still quite fascinating because of the high resolution that you can get this way.
Right. Yes, and you were saying from the beginning that sort of the larger your aperture is, the better becomes the precision. Then, since you sort of have a huge aperture that might surround the user, but there is big holes in between the access point, do you create a lot of messy ambiguities from that,
indeed.
or grating lobes?
You will for sure. So again, I mean, what I said here is fundamentally, if the signal to noise ratio is high enough, then the accuracy will be proportional to the size of the aperture, which in the distributed case would be determined essentially by the distance between the access points rather than by the aperture of an individual access point in itself. So number one, signal to noise ratio would probably have to be rather high for this to work in practice. And number two, there'll be a lot of algorithmic challenges in actually finding the position estimate.
Yeah, it sounds like calibration might be one of the issues here when the antennas are far apart.
Calibration certainly will be one of the issues. I mean, because if these access points are so basically there are two cases. Either the access points are driven by a common clock or a common frequency reference source, and in that case, one would have somewhere an oscillator or a clock that generates this reference signal, and that reference signal would be distributed through a cable to each one of the access points. And that way they would be all phase coherent. There would still be an unknown residual phase offset between them, but it could be estimated, for example, by using a reference receiver or transmitter at a known location and then applying some algorithms. So that's the first option. The second option is that the access points have free running oscillators that aren't phase locked to one another. And then there will be a phase shift between the access points that drifts over time randomly, depending on how good quality these oscillators or clocks are. And this drift can be quite fast. I mean, for reasonably priced oscillators, we're talking about drifting halfway around the unit circle here in substantially less than a second. So some sort of periodic recalibration would then be required. And it could be done using reference transmitters or reference receivers, or in combination with bidirectional measurements over the air between these access points and so forth. And this isn't an easy problem. I mean, so of course we have a similar problem for calibration for cell-free or distributed MIMO when we use the access points for calibration. But there we only need joint reciprocity calibration between the access points, and that's much easier to accomplish because they can be accomplished by using a bidirectional over-the-air measurement between the access point without knowing their locations or the distance in between them. Whereas for positioning, we would need side information for this calibration to work out. But it's a fairly technical topic, and maybe that's something we could save for a potential future episode to talk about in detail. But the main take home here is that calibration will be required, and that's a non-trivial thing to accomplish in practice.
Right. So one of your point there is that if you deploy a distributor cell-free MIMO system, certain calibration is already needed to make that whole thing meaningful to deploy. But beyond that, you need to calibrate it even further to utilize these services.
That's right. I mean, that would be the most simplified way of stating the point here, I think that for cell-free massive MIMO to operate in TDD with reciprocity-based beamforming, a certain reciprocity calibration is needed between the access points. And that reciprocity calibration can be done through over-the-air measurements, but that isn't enough that isn't enough to calibrate the system for positioning. So then something more is needed here that requires known distances and or reference transmitters or receivers located at known positions. But again, this is a fairly technical topic that we might want to return to.
Sure, but so this is certainly theory. Have people been able to do something like this with some kind of practical
absolutely, and that was another thing that I learned and that was very impressive to see at the Symposium. So co-located with the Symposium, there was also the ELLIIT 6G Focus period where we had 3 weeks of visiting scholars who spent 3 weeks there on site working together on many projects. And one project that one of the teams worked on was exactly on positioning and synchronization for positioning using distributed antenna systems. So what he had done was that he had used experimental data from a system where there were, I think it was 8 or 10 or something, distributed access points that were placed at like known fixed locations. And then they had a mobile transmitter they could move around. And the goal was to estimate the position of this mobile transmitter and track it over time using carrier phase measurements to the access points. And these access points, they were all phase locked using a common clock that was distributed through a cable, but they still had to work out this residual phase offset between the access points and estimate that jointly with the position. And this all worked, and it was really fascinating to see. And impressive to see the work that they had done during these weeks.
Right. Yeah, I think it is easy to, or not easy in general, but developing theory is sort of one thing, but actually demonstrating that things are working in practice is really one of the big challenges as well.
I would put it this way, that some of the theory that we tend to develop is just simplified in that it ignores a lot of practical phenomena that will be there and will have to be dealt with, and some of which have a lot more like intellectual depth than what seems at the surface. Like, for example, phase offsets are easy in a way to model theoretically. They will be there and they will have to be dealt with. Phase drift, unless the oscillators are locked to each other. And there'll be other effects like drift of the sampling clock that results in a time shift between the samples that needs to be estimated and compensated for. And there's a lot there in the algorithmic space that sometimes in the COM theory literature, I think we are ignorant of or not entirely willing to dig into, but which in practice often constitutes the limiting factor on what you can actually do.
Yeah, I think now when we are entering 2024, we sort of 5 years into 6G research perhaps, and then I hope that there will be more and more experimental works also starting to validate these type of things, because I think when it comes to technology transfer from academia to the industry, if something is really groundbreaking, we also need to be the ones demonstrating it in the lab, that something works. Otherwise, the industry will not pick it up.
Yeah, so where do we go from here, Emil?
I think we will talk a bit about machine learning.
Machine learning. So what's new in machine learning?
Right, so I was picking up some things regarding machine learning that from a talk by Anders Persneira that was not actually focused on machine learning, but it was still very intriguing to me. So as many others, I was studying about neural networks some years ago when the hype on machine learning was taking off in the communication area. And this name neural network or artificial neural network is sort of demonstrating how you are developing deep learning to be inspired by the brain. But then when you are reading more and more, you realize that this kind of connection to how our brain works, it is kind of motivational or vague. It's not like actually copying what the brain is doing is what actually matters. But the typical structure of a neural network is sort of, okay, you have a number of layers that do some linear processing of data, and then in between you have what we call activation functions that do some kind of non-linear processing. And then you go to the next layer, do some processing, and so on. And then you optimize what every such layer is doing in this linear processing part. But the activation function is typically something that is picked in advance. And I think the whole name activation function is sort of inspired also by the brain, that neurons in the brain, they collect different signals, and then if they the signals that are reaching them is strong enough, it's firing away some signal to the next location. So it's sort of, you want something that sends forward nothing, and then it sends forward something according to a particular shape, and there's often like nothing and then a linear version of the input. So you either block it or you send it through, or there is some S-shaped or some different kind of shape there. And what Anna was talking about was why do we actually predefine from the beginning or select what this activation function should be? Do they need to have this kind of monotonically increasing shape, or could it just be any nonlinearity there? Because often when you see works on this, you see, we picked a relo, or we use a sigmoid function, or this and that, and you ask the question, why did you pick this? Well, it worked.
I mean, it feels like this ought to be well investigated in the, let's say, hardcore machine learning literature, right? What activation functions that would work well in practice.
Yes,
but I'm not sure how well.
Exactly. So I think there is a huge amount of sort of work on what works and what doesn't work. Still, I haven't seen the things that Anna was talking about, namely to parameterize this activation function. So he was using a discrete cosine transform function which can sort of approximate a lot of nonlinear functions and have some trainable parameters. And you can then also train these activation functions. And whether this gives you very useful new kind of degrees of freedom to design neural networks or not, I'm intrigued to understand this better, because it doesn't seem to be used very much. But it seems like a logical thing that you should do. So you start to wonder, why is this not the way that everyone is doing it?
Right. Yeah, that's something I don't have really a lot of intuition for, and that I would need to really read up on. But it sounds like an exciting prospect. You could actually optimize these functions in addition to the weights in the network.
And at least there were a nice use case of this that she was describing. So there is this kind of learning over there where you have IoT devices that are collecting some data and report them up to some server. And one way there that she was noticing is that this discrete cosine transform, this is essentially what the waveform you're sending in LoRa, which is sort of one of these IoT communication systems.
Right.
So
it's basically frequency modulation, right? But in discrete time,
Yeah. So if you design a neural network where every IoT device takes care of some of the layers, and then they report their signals up towards the server, and when doing that, the signal sort of sent with this cosine transform. So over the air, you do this activation function, and then you can have the final layers in the server.
Yeah, that's a real cool thing. Yeah.
Yeah, so I was really sort of intrigued by, this all makes sense. Why are not people doing this? So this is something I will really like to look into more to understand.
So this is like federated learning over the air, but in a broader sense, right? You apply nonlinearity on your signal before you transmit it. And in this case, the nonlinearity is this frequency modulation or discrete cosine transform.
Exactly. So whatever non-linear function, you can approximate it in this kind of way with a few parameters. So if you want to design activation functions that are not just something that is monotonically increasing with a predefined shape, well, this might be the way to do it.
Right. Yeah, it's quite intriguing. I mean, this with machine learning, both the like enabling methods and theory and the applications of it.
Yeah, and it's very much this kind of craftsmanship of figuring out what can be used to improve on previous works. So did you pick up something regarding machine learning?
Yeah, so there's a talk on reflecting intelligent surfaces, and they're using machine learning algorithm to train the way that the weights are adapted, because in a reflecting surface or RES, so it's actually reflecting intelligent surface, or is it reconfigurable intelligent surface? People seem to use both, but it seems like the abbreviation RES is in any case adopted for both. So the idea was because in a RES then you have all these small atoms that need to be individually controlled, and basically for each atom there's a phase angle or the load impedance that need to be set. So there'll be like a humongous number of parameters that have to be tuned for the RES in order to reflect or scatter the signal into the desired direction. And nominally, I mean, if you have a transmitter and a receiver and a RES, you would need to send as many pilots, orthogonal pilots, as you have atoms in the RES. And that would cost a lot of resources, because the RES, by nature, it will have to be large and consist of many atoms in order to actually give any array gain. So that would cost a lot of pilot resources. But what were done in this paper was that they optimized the machine learning algorithm to... The way I understood is like the algorithm basically learns what the environment looks like, so that the RES can be configured using only very short pilot sequences. And it was quite fascinating. I mean, because one of the hesitations I've been having a little bit to RES is precisely this problem that you'll need a lot of training overhead to configure the atoms. And now if this could be done using very short pilot sequences, then in a way, I mean, the problem would be solved, right? Of course, what the story maybe didn't fully tell is like, what if the environment changes? So even if I just change something small, I move this little vase here slightly away, then will I need to retrain then the algorithm, and how long will that burn-in time be before the algorithm actually delivers, and these short pilot sequences are enough to configure the RES? But I found it to be a neat use case of modern machine learning algorithms applied to what I think we can argue is the physical layer, really, of wireless comms.
Yeah, I was also sort of thinking a lot about this thing with how many pilot resources you would be needing to reconfigure these very big surfaces, as you were saying. I think we wrote a paper about RAS about 3 myths and 2 critical questions, and I think one of the critical questions was, how can we estimate these things reasonably well when we have so many parameters? And
yeah, I mean, there's a scalability problem, right? Because for the RES to be useful, it has to be large, maybe very large indeed. And when it's very large, it means that it has many of these atoms that need to be adjusted. So you'd need correspondingly longer pilot sequences in order to estimate a channel and train these coefficients.
Yeah, and I think there are sort of 2 things that machine learning can do in this case. One is to sort of learn a better estimator so that you use some information about the environment to boost your SNR, essentially. So you only focus on estimating the important things and get the better estimate of that one. Then if you should also be able to sort of cut down on your number of pilots, so you ignore exploring certain dimensions of the channels because you know something about how the different dimensions are connected to each other, then you use even deeper knowledge there. And I think one of my the fact that they were really able to reduce the pilots immensely here is sort of showing that there is a lot of structure in the channels that they're considered. And this is something one can possibly utilize also classical signal processing methods, compressed sensing, or angle of arrival estimations and these type of methods.
Certainly.
Also,
I mean, isn't it that again? I mean, the algorithm basically learns what the propagation environment looks like, and say, I mean, for the sake of argument, that the algorithm could learn exactly what the environment looks like, then in principle you could like you could solve Maxwell's equations, so you could ray trace or something, so that you just need a single pilot symbol and the rest where you know where you're located, and then configure itself accordingly. So it all comes down, I think, to like how much of prior information that the algorithm either magically knows or has learned from measurements or from experimentation about the environment.
Yeah, no. So I think this is also an area where I think experiments will be really nice to see in the coming years to benchmark machine learning approaches compared to classical line of sight estimation problems from our maximum likelihood estimators with array response vectors and stuff like that, and possibly some mix of these things, like what people call physics informed machine learning, where you sort of try to extract knowledge that you know exists physically there, but then you also learn how to improve the performance. So it would be interesting to see how this works out.
I agree, and I mean, experiments are really required here, I think, because it'd be difficult to model a simulation environment accurately enough to really to really capture all the fine details that these algorithms eventually will break or make the deal in terms of how well they work.
But the great thing is, at least, that I'm hearing more and more about people who are building these surfaces, and I mean, building something that reflects in an unusual way is not that hard. People have been doing that for a long time, but also having the configurability features there. So hopefully we will see this kind of things in the coming years now.
Mm-hmm. Yeah, neat. Okay, so what do we have from here, Emil? Maybe communication theory. So was there anything in like hardcore comms theory that you learned from somebody talks?
So I saw for maybe the second time a talk by Muriel Medard on GRAND, which is an algorithm or approach to decoding data that she has been developing together with people. And GRAND stands for Guessing Random Additive Noise Decoding.
Guessing Random Additive Noise Decoding. Wow. So how does this work?
So I think I will start with describing just the premise of this, that when you have a mobile device that is connected to a number of different wireless technologies, then each one of these ones might use different types of channel codes to protect your data transmissions from errors. And for the normal approach is that for your channel code, you develop an optimal or approximation with reasonable complexity, close to optimal decoder. So you utilize the structure of the code and try to guess what is the most likely code word that was transmitted given what you received. And this is what we also teach in a lot of courses. The problem might be when you're sending a lot of data, that you need to hardware accelerate these type of things. You need to build silicon that is doing the decoding. And then if you have 6 different types of codes, maybe different lengths and stuff like that, you might need quite some different pieces of silicon to do all of this different decoding. And what Medard tries to do is to develop one universal decoding algorithm that can be applied to a number of different channel codes.
So let me see if I understand this properly. So are you suggesting here that the goal is not really to squeeze out additional fractions of a dB in performance, like to get closer to channel capacity, but rather to build a decoder that could be more universal and function more easily with codes of different rates and with different channel codes simply?
Yes, exactly.
So it's more like an implementation. So the advantages would be more on the implementation side.
Yes, exactly. So for that reason, they are both working with information theory to sort of prove that certain that you can decode codes in unusual ways that happen to be similar for different codes, and work with designing one circuit that can decode a number of different types of codes.
One circuit that can decode a number of different types of codes. Are we talking about like short blocks or long blocks here? Do you know that? I mean, how long? Because
as far as I've understood, it is fairly short or medium-sized codes, but not extremely long that they have been doing so far. But I'm not entirely sure about this. But I think the main principle then that this goes into the name, so guessing random additive noise. The idea is then that since every type of code that you design have a particular structure, the normal approach have been to utilize that structure and develop a decoder based on this. And then that naturally leads to that you need a different types of decoder for different codes. Their approach is instead that instead of directly use the structure of the code, you instead try to guess what kind of perturbation might the noise have done. And the basic thing would be, okay, you send 10,000 bits. Is it the first bit that is an error, the second, the third, and so on? This would be different types of noise errors that the noise can have caused. And then they take your received signal, they subtract these different guesses of what the noise might have been, and then they check if each of these things happen to give you something in your codebook of original possible codes.
So it sounds like a brute force kind of approach to decoding. I mean, isn't okay? This is getting very technical now, but it seems like the number of error patterns you can actually get would grow like exponentially.
Exactly.
So yeah.
I think normally the whole point with channel coding is that you have a large number of possible bit sequences that could have been transmitted, but you only pick a small subset of that. And you try to make those ones as different from each other as possible to have a natural distance between the different code words in whatever way you measure that, Hamming distance or something else. And then you then utilize this distance between them so you can correct errors. So naturally, there is many more possible noise sequences than there are signal sequences. That's the whole point. So the real requirement to make this work is that you can actually make a good ordering of noise sequences so that the first ones you're checking are with extremely high likelihood providing you with the correct decoding.
So you somehow need to sort the error patterns according to their in descending order of likelihood somehow, and then try them one by one, and relying then on the presumption that given that you try like a fixed number, then with very high probability actually capture the actual pattern that you saw.
Exactly. So that is really the essence there, and how you order this noise sequences. This is not entirely transparent to me when I'm reading up on this topic. Maybe it is just that, okay, if you expecting one or two errors, well then you try to place them where your log likelihood ratios are something regarding that. But it becomes technical, and it's not entirely easy how that is done. And I think this is also why the research is still ongoing on this topic. But if you can order noise sequences in a convenient way, you can try to subtract different ones. If you have a way of checking if the result is a code word in an efficient way, well, then you're home.
Then you'd be home. Yeah, that I agree. Okay, yeah, that sounds like something worth reading up on and understanding in more depth, I think.
Yeah, and I think also here, at least the nice thing is, as I was saying in the beginning, that this is not only information or communication theory, they are actually building these type of things, and I think their circuits are from generation to generation handling more and more codes. So let's see how far they can take this in the future.
Yeah, that'll be interesting to see. Wow. Great. So anything else in comms theory at the symposium that caught your interest, Emil?
Yes, I heard Christoph Studer talks about jamming and MIMO, which interests me because I was, maybe together with you, doing some research on this some 5 or more years ago. And I think one of the things that we are sort of now taking for granted is that in the next generations of wireless systems, we will use more antennas. And we will probably use more bandwidth, or at least we want to handle many more spectral bands. And then people liked to cut down on the hardware resolution, or at least not scale it up in the same way. We know, okay, we've increased the bandwidth, we need to sample more quickly, but every sample needs a certain number of bits to describe the signal that we're seeing. And instead of having a few samples from a few antennas with 15 bits per sample, maybe we can get away with 3-4 bits per sample per antenna because we have so many antennas. And people like both of us have been working on this and demonstrated that, yes, it works. You can actually get away with this because the total number of bits is so many, as long as you only consider the communication performance inside your band.
Well, I'd say as long as you assume a priori that you're perfectly synchronized in frequency and maybe time, then, and you ignore like other effects, like for example, out of band transmitters that might come in as blockers. And I mean, typically you'd have like a digital filter that, a band pass or low pass filter that suppresses everything that goes outside of the band. And we assume that magically somehow all those aspects have been solved in some other way, then you're right. I mean, we can get away with a single bit or a couple of bits, a few bits of quantization per IQ branch. But I think it remains to be seen whether these very coarsely quantized ADC transceivers can really work in practice, all things considered.
Yeah, and this is really what Christoph was talking about, and maybe his focus was on some malicious transmitters that try to jam your system and send some strong signal that would sort of be stronger than your desired signal.
Right, and now we're talking about the malicious jammer in band here, not even out of band, right?
Yeah,
because one of the difficulties with low resolution ADCs is to handle out of band blockers, but now we're discussing like intentional jammers in band that could maybe be, is that even worse, or so how would that be handled here then?
I think this is certainly one of the weaknesses with this low bit ADC resolution, and it sort of comes back to why have we been using a high resolution in the past? Well, to be able to protect ourselves against blockers or jammers or whatever that might show up there. And what is the solution to this? Well, to a large extent is signal processing. You want to sort of remove these jamming signals from what you are observing. And then you have the issue that if you do this after you have sampled, you have this low resolution, and you can choose sort of the range of values that you have in your quantizer. So either you keep the same range as you would be having without the jamming, and then there is a risk that the jamming just saturates, so you'll only see the maximum value all the time because of the jamming.
Because you just don't have the dynamic range here. I guess that is the core
exactly.
of it.
Or you adapt your dynamic range so that you can actually see something, but that will of course still mean that you have very coarse resolution on your signal. So
that's
you have
right. I mean, dynamic range I think is just simply proportional to how many bits that you have, and then you can adjust your AGC to shift where the window is located.
So you have very high step sizes, you still have very poor resolution. So what Christoph was describing was two ways of trying to deal with this in the analog domain before you quantize the signals. And I think this is probably the way to go here. So one approach was based on that maybe inspired by hybrid beamforming approaches. So you have circuitry that takes your signals from the different antennas, and then they is turning this into beams coming from different angular directions. So you look in this in 30 degree, in 0 degree, minus 30 degree, and so on. And in these different directions, whatever way you build it up, you extract the signals. And since the jamming signal mainly comes from some specific angles, you might be able to sort of throw away that directions and not communicate with anyone in the similar directions, but at least from all other directions you can sample signals with low resolution that are still useful.
But it's a pretty clever idea. I mean, it sounds like some sort of analog pre-zero forcing approach where you using analog electronics filter out the spatial window that you want to look at, and then within that window you can apply then your favorite digital algorithms. But I guess a way to defeat this would be if the jammer comes in from many different directions, or the jammer actually consists of an array or a bunch of geographically separated transmitters. That would be a challenge. Yeah. Let alone if the jamming signal comes in from nearly the same angular direction, this wouldn't work either, right? But then, of course, the digital method will also have a hard time, because with zero forcing processing, even with infinite resolution of your AD converters, it would be a challenge to separate out a jamming signal that comes in with a channel that's nearly parallel to the channel of your device of interest.
Yeah, so there are certainly cases that will be so complicated that you can't deal with them. But Krista was also describing a way of doing this that was a little bit more clever. So if the first one was just divide directions into different windows and throw away the directions where there happen to be a jamming signal, he also had some algorithms that are sort of like a feedback loop. You try out to sample different directions and then you feed back to the analog, okay, tune the processing you're doing there in a way of trying to get rid of some zero forcing. To implement some more zero forcing, like based on where the jammer actually is, to fine-tune things there. And at least if the jamming signals are relatively stable from which channel directions they are coming from, you might be able to make that work as well. Right, but I think it remains to be seen if the bit resolutions will be reduced in future systems, or if this is more like an academic thing that people are doing.
Yeah, I concur. I mean, but there are great incentives in terms of power consumption to cut back on this resolution. Because as I understand, I mean, it's like exponentially more expensive when you add bits to your ADC than, both in terms of the circuit complexity, but also in terms, maybe more importantly, of the power consumption of the circuits.
Yeah, definitely.
So if this could be made work in reality, then that should be highly useful.
Exactly. So a lot of the other power scalings there are linear. So add another antenna, or double the number of antennas, you double the power from the ADCs, and double the bandwidth, and you double the power consumption. But here it's actually exponential. So,
Wow. All right. Very good. So I guess that was it for the comms theory then. Anything else that we learned from the symposium? I think there was also a session on spectrum use for the future, and a couple of talks that dealt with electromagnetics and energy efficiency. Want to talk about spectrum?
Yeah, I can take my last of my 5 points here, which was related to spectrum. It was also Stefan Parkvall from Ericsson who talked about this. And I think after this talk, there's also been the World Radio Congress. The countries of the world are meeting to discuss what kind of spectrums to use for different type of radio technologies in the future. And I think that there has been a lot of discussions about new frequency bands that can be used, because it's always easiest to create a new, like 6G technology in a band that haven't been used for 5G or 4G or 3G before.
So you mean like creating like an entirely new radio interface then in a new band? Is that what you mean when you say creating a new like 6G?
Yes, I think that's often when we are deploying, say, 5G, we do this not by tearing down existing base stations and use their spectrum, but we actually allocate new frequency bands. So we can do a new deployment that use those bands, but still keep everything we had. And if we should keep doing that in 6G, well, we need to find new frequency bands that we can use for 6G. And there have been all kinds of discussions in the past 5 years, from sort of, a lot of talk about terahertz frequencies, so go beyond millimeter wave frequencies. So if the millimeter wave frequencies in 5G start from, say, 26 and goes up to 80 gigahertz, then if you go beyond that, people call this sub-terahertz. So there's a lot of research going on there, and this is really a place where you are challenging hardware design a lot.
Well, not only the hardware design, I think you're actually challenging the physics as well, right? Because the link budget is horrible, and also Doppler is so high that it'll be very difficult to do anything. To channel estimates will be outdated very quickly if there is any mobility at all.
Right.
Yeah.
And I think the whole talk about this sub-terahertz area in the past years have sort of been based a little bit on the misconception that whenever you are designing a new standard, we need to go up in frequency. So from 3G to 4G, from 4G to 5G, we were using progressively higher and higher frequencies. And then what will be the next thing? Well, we need to go beyond the millimeter wave frequencies. But Ericsson's view, and I've also heard it from other companies, is that no, we should look into the hole that is between the two frequency ranges used in 5G. So they have the range 1, which goes up to, say, 6 gigahertz or so. So we call the sub-6 gigahertz band. And then we had the millimeter wave frequencies that I was mentioning, which they call frequency range 2 or FR2. And in between there is an interesting frequency band, particularly between 7 and, say, 15 gigahertz. And this is the area that Ericsson called the centimeter wave band. And
a centimeter wave. So centimeter wave is between, you said, 7 and 15.
Yes, and you can probably take the term centimeter and say, when would you measure things from 10 to 1 centimeter, and say this is centimeter band. But I think they particularly like to use this term now for this band that is in between the two ones considered in 5G.
Is that the same as the mid band? I heard that term being used also in the past.
Right.
So mid-band and centimeter band are the same, more or less, here. So 7 through 15.
To some extent, I think actually the mid-band have been, say, between 2 or 3 gigahertz and up to the maximum we have been using, so say 5-6 gigahertz. But now, when they introduce this centimeter band, they start to call this the upper mid-band. So
the upper mid-band.
Yeah, so that is also an alternative name there. So if most of the 5G deployment is in the mid-band, if we will expand 6G into this new bands here, we will have 5G in the lower mid-band and 6G in the upper mid-bands. And the issue is, of course, in general, that frequencies are used for other kinds of services already. And there is a lot of things there, for example, for satellite communications that is going on already in these frequency bands. So you really need to agree in the world on what frequencies to use in the future. But at this World Radio Congress that was held recently, they actually started to take steps towards using some of the spectrum. And the way that this works is that you need to at one Congress decide on, we will look into using these bands for new purposes and see how that will work with coexisting with existing services. And then 4 years later, when you have the next Congress, you can decide on actually changing the use of spectrum for new services if you think that works out. So, what they did was to say in 6.4 to 7.1 gigahertz band, that has been sort of a little bit earmarked towards 6G and to looking in if you can use that. But there are also some other bands around that also going up towards 15 gigahertz that are sort of being analyzed now until the next Radio Congress for coexistence.
Yeah, it sounds like a real challenge to get the countries in the world to agree on what bands to use for what purposes here.
Yeah. And the world is also divided into some different regions. So it might be that there will be some frequencies that are used all over the world for 6G, but also that different regions will have some specific frequency ranges that are specific to those ones. And fortunately, in the past, it was really hard to build hardware for mobile phones that can handle many different frequencies. And they were like the dual band and triple band 2G and 3G devices. But nowadays, you can build devices that functions over quite large frequency ranges. So it will hopefully not be a problem from that perspective.
Yeah, I can imagine. I mean, this poses enormous challenges on the analog electronics. You'll need very flexible demodulators, mixers, and bandpass filters, let alone the antennas. Typically antennas are tuned to particular bands or carrier frequencies. So the more different bands there are to be supported, the more complex will the circuitry become as well.
Right. But at least I think the interesting prospect here is that if we sort of double the carrier frequency from the 3.5 gigahertz we use today in 5G, then we can have more MIMO and we can have better resolutions for different kinds of positioning and localization sensing services, and we can still have reasonable range, but there might be some of these very optimistic 6G goals regarding 1 terabit per second per device that we will never reach in those cases, but maybe that is fine.
Yeah, maybe that is fine. I mean, of course, to reach this terabit per second, you would have to go up in carrier frequency simply because you need a lot of bandwidth, and that bandwidth is only available up there. Then I suppose it could be debated how important those use cases really would be in practice, and whether perhaps it's rather coverage and uniformity of the quality of service that will be important. And then, of course, lower carriers have great advantages.
Yeah, I fully agree. So did you pick up anything when it comes to spectrum and electromagnetics?
Yeah, I mean, so there was some discussion in one of the talks on energy efficiency, which obviously in a way has always been important, but it appears that it'll be increasingly even more important for 6G. And I think part of this is just a consequence of the fact that if we build larger and larger MIMO arrays and use more and more bandwidth, there'll be like more and more signals to process, and numbers here are staggering. I mean, so one number I heard was that if you have like 1,000 antennas, which is 10 times more than a massive MIMO base station today, but not in any way off the wall, I mean, in terms of what could be built. And I think it's the vision of these large intelligent surfaces, not reflecting intelligent, but large intelligent surfaces with actually active electronics at each antenna.
Yeah, so MIMO arrays.
Yeah, MIMO arrays. That you could easily comprise like 1,000 antennas, and it would use maybe like 100 megahertz bandwidth. So then you'll have an interconnect in the backhaul would be on the order of terabit per second, and just the memory requirement just to store the channel estimates in an OFDM block would be like in the order of a gigabyte or gigabit or gigabyte. So there'll be enormous demands on the signal processing here, which in turn, I mean, processing costs energy. So this will be an important aspect to actually design algorithms that are efficient, and then to build the products to not burn a lot of power in idle mode. Because as I came to understand some of the like network equipment or radio base station access points you buy today, they burn a lot of power in idle mode. So it's like the power consumption isn't proportional to the data traffic load. It's rather that they burn a lot of power in idle mode, and then when you actually transmit something, they burn a little bit more. But you would rather expect that when they are in idle mode, they burn nothing, and then the power consumption grows like proportionally with the data traffic. So to what extent that's a research problem or more of like an engineering implementation problem, I don't know. But I think we ought to be aware of the fact that energy efficiency is a major is a major and will be a major issue in 6G. And this concerns both the digital processing and handling all the data on the backhaul and all of that, but also the analog front ends. I mean, and there are of course power amplifiers, one of the main culprits. So for example, at the millimeter wave band, as I understood, the power efficiency of an amplifier could be on the order of 10%, which means that for every unit of energy we put in, only 10% goes to something useful, and the rest of the 90% becomes just burned or dissipates as heat. So this is, I think, something to be aware of, and something that we in comms theory research should always keep at the back of our head, that
I think we talked about energy efficiency to some extent in the previous episode as well, and I think one of the things that people have been working a lot with 5G is different kinds of sleep patterns, where you try to turn off as much equipment as possible to reduce these idle mode things, and I think there are improvements happening there, so that it possibly not going to be the weakest spot anymore, hopefully, in the 5G and 6G, but if the whole goal is to build a technology that transfers so much more data, then the data the power consumption will grow at least linearly with the data rate in those cases. And then, if you go up in frequency, hardware becomes less efficient. You have all these issues you described. And I think 1,000 antennas might sound far-fetched, but if you think about today, a base station with roughly 100 antennas, and then you triple the carrier frequency up in the centimeter wave range, and then horizontally 3 times more antennas vertically, that 9 times more, and you start to come up to 1,000. So it's not at all far-fetched.
No, not at all. I mean, this is good that you underline that point. In fact, and also concerning power spent in idle mode and all of that, I mean, it isn't obvious to me how much this is really a fundamental problem. Like, is it that we need better protocols on like higher layer to determine when to sleep and when to wake up, or is it just that the software and hardware implementations need to be better, so that, I mean, if you compare to the personal computer industry, for example, then it used to be that a Windows PC could take 10 minutes to restart, whereas the MacBook, you open the lid and it's on. And the question here is whether is it just a matter of implementing the software and maybe hardware properly, or is it a matter of actually resolving and designing new protocols for how these devices should interact with each other, and determine when they should go to sleep and when they should wake up? And
I think I have colleagues here at KTH who have been working on using machine learning for this kind of thing. So even if you develop protocols or implementation that have different sleep levels, where you can go deeper into sleep, in those cases you save more energy from when you're idle, but it takes a longer time to wake you up and get everything up and running again, then it's really you don't want to go to deep sleep when it's not needed, so you need to wake up and create delays, but you want to be in deep sleep as often as possible. So this is something where you can try to learn something about the traffic and turn things off. And
absolutely. But also, I mean, my point is that is there any fundamental reason for why it should take a long time to wake up from deep sleep? Maybe it does for humans. If you wake me up at 2 o'clock in the morning, then it's like, it'll take me 5 minutes before I'm like in the game. But for a base station, you could have everything like prefetched in memory somehow, so that once he wakes up, it takes a millisecond and then it's operating. So it isn't clear to me that it really has to take a long time to switch between these states.
No, it could possibly be synchronization then of analog hardware, like the thing we talked about earlier with having distributed access points that should be phase synchronized enough to do some particular features.
Yeah. Wow. All right. So anything else, Emil? So there's one thing that I was fascinated by, and that was brought up in a talk on RIS again, but the angle here was that, so as I understand, I mean, RIS can be built from just components that we know from like classical antennas, right? You basically build patch antennas, and then you connect them to a load with a variable impedance, and that in turn can be implemented using standard components like switches and diodes and other things. But there's also this notion of meta materials, or electromagnetically active materials, and as I understand, I mean, one use case for these materials is a way of implementing a REES. But there are also materials that go way beyond what you would need for a REES. So, for example, there was talking of metamaterials that could perform like signal limiting. As I understood, that meant simply blocking waves that have a higher amplitude than some thresholds. So there would be some highly nonlinear characteristics here. And there was the notion of a Doppler cloak that, I don't know if I understood this fully, but my impression was that the metamaterial itself could modulate the signal to undo, at least in part, the effect of a Doppler shift. Were you able to grasp, maybe better than me, these concepts? It sounded like super exciting, and it was really something new that I had not thought about or even known about beforehand so much.
Yes, so I think you picked this up from a talk by Peter Popovsky, and I've been working a little bit with him on some papers in the past. I know that he sometimes talks about non-linear propagation environments. And I think, as you were describing, you can view each element in this RIS as, so it receives a signal and then it has this impedance. There's a circuit that is sort of where the impedance might be phase shifting the signal before it gets reflected again, depending on what impedance level you have, and it might change the amplitude and stuff. And in principle, you should be able to put other kinds of analog components there as well that could be processing the signals. And I think one option would be, if this kind of impedance is sort of fluctuating, it starts to give you a nonlinear behavior that could, for example, also modulate the signal and move it in frequency. So I think that the Doppler cloak is really about that, okay, the signal is shifted in frequency because of Doppler shift, and then you let the material shift it back.
Wow. Yeah. So, I mean, this sounds super exciting. My only hesitation now, being a little conservative, is that we're introducing non-linearities and we're introducing time variation, right? So we work so hard to get rid of or minimize the effects of non-linearities. For example, in power amplifiers, and we talked earlier about this ADC converters, where obviously the less resolution we have, the more of a non-linearity there will be. And one reason for that is to avoid out-of-band susceptibility to blockers out-of-band, or avoid generating in a transmitter and generating out-of-band radiation, right? So now if we introduce metamaterials that are non-linear, then it seems to me that suddenly we could create all sorts of new problems with out-of-band radiation and out-of-band compatibility that's not clear how to handle. And also, if we start introducing time variation, then we'd break reciprocity, right? I mean, also we work so hard to ensure reciprocity, because that's what makes massive and cell-free and distributed MIMO work with time division duplex and reciprocity-based beamforming, so that we can rely on the fact that the propagation environment is reciprocal. And as a fundamental property of electromagnetic propagation, as long as there aren't any non-linearities, or as long as there isn't any time variation, or there's some oddball materials, they can break reciprocity. But we work very hard to ensure this reciprocity. Now we would put up metamaterials there that start to fiddle around with time variation of their characteristics and non-linearities that would break all this apart. So in any case, this is super, super exciting technology, I think, to learn more about.
Yeah, there is certainly opportunities of messing up a lot in your wireless communication systems by introducing nonlinearities, which we usually want to avoid. We recently wrote a paper just about the fact that if two telecom operators deploy one RIS each, and they start to fine-tune each RIS for their own purposes without caring about the other, operator, then even if there is no signal leaking between the two bands, they are changing each other's propagation environments.
They're changing the propagation, and then we're talking about still, RIS is time variant, but on a very slow time scale, right? But it's, as far as I understand, substantially linear. It doesn't introduce non-linearities, but it does introduce a very slow time variation. But even then, without any complicated metamaterials with non-linearities and all of that, you could create a complete havoc in the ether.
Yeah, so I think the paper that I wrote with Peter on this was sort of based on a very long set of sort of maybe unrealistic assumptions. But suppose you have an abundance of bandwidth, you don't really care about causing interference to anyone else. Maybe this is terahertz or whatever. And then we talked earlier about the issue with channel estimation, that the more different elements you have, the more parameters you have to estimate. But what if you have different groups of elements that oscillates in different ways, and instead of trying to cancel a Doppler shift, you actually just want to move the signal in the frequency domain so the receiver sees it at a different frequency. Then all of a sudden you can transmit in one band and you can observe it in multiple bands at the same time, and then you can estimate all these parameters at the same time.
Yeah, it's quite fascinating. I mean, there's entirely new possibilities that open up here.
Yeah, whether there are gains or not is a different question, but I think this is also what we in academia should do, explore what you can possibly do physically and if there is any gains from it. So
that's right. Yeah, sounds like an exciting research direction to go for the future.
Definitely.
Yeah. Wow. All right. So maybe it's time to wrap up here.
Yes, exactly. And I hope you have also been, as a listener, as excited about some of these new topics as we have been. So thank you very much for listening.
Yeah, that was a fun session. Thank you, Emil.